This is a Sutotal production.
Hello, Chem Minions. Sutotal coming at you. This is going to be our third practice for Chapter 4. And so here what I've done is I've given you a few pairs of molecules. So each set of molecules in the box, we're going to look at them and we're going to try and determine what's their relationship. Are they a pair of enantiomers? Are they a pair of diastereomers? Are they just the same molecule, just shown to us differently? Or are they, in fact, constitutional isomers? And don't remember, constitutional isomers, we change the connectivity of stuff. So that's going to be kind of the big difference. Constitutional isomers and enantiomers, diastereomers, and identical, because a lot of the connections are the same. It's just the stereochemistry is different. All right, so here we go. As we take a gander, here we have an alcohol. So this carbon is definitely our chiral carbon. And we see that our OH is in plane with this propyl group. And we have a methyl group that's wedged. And if you notice, like if I were to pretend that there was a mirror right here, this would in fact be the mirror image of it, right? Both the methyls are wedged, the OHs are closest to the mirror, the propyls are the farthest away. And so if we go back into thinking about what is the definition of an enantiomer, it is a non-superimposable mirror image. How do we know that it's non-superimposable? We look for a chiral center. 1, 2, 3, and there's a hydrogen. So there's 4 different groups at that chiral center. And this is given to us as a mirror image. So it is in fact a non-superimposable mirror image. So this is definitely a pair of enantiomers. All right. Next up, here it's not really shown to us as a mirror image, but if you notice, everything's on the same side here, right? Not the oxygen, but the alcohol groups are on the right, the propyls are on the left, and then the methyls are pointing up, and they're either a dash or a wedge. And so if we were to, in fact, take this guy, right? Imagine it's this part of my hand, and I just flip my hand over like so. Right, it would look exact. So this flipped over would look exactly like that. And so this is yet again just another pair of enantiomers, or as some would say, enantiomers. I'm going to say enantiomers. All right, I'm almost as country as cornbread, so enantiomers. All right. Anyway, so with that, next up, what do we got? Dang, I'm really enjoying these alcohols. All right, so here we have a third set. So it's the same alcohol, but now you notice right here, if we had that mirror image, that both of these methyls being wedged, they would be enantiomers. And if we pretended that there was a mirror image here, both the methyls would have to be either dashed or both would have to be wedged. Now, if we look at this, right, if we do this comparison for this third group, right, I went ahead and put this line here to show like the mirror image, but this isn't a mirror image, right? Because here this methyl is a dash and this one is a wedge. So these actually aren't enantiomers. And they can't be diastereomers because you would need at least 2 chiral centers to be diastereomers. And so the real question is, are they identical or are they constitutional isomers? Well, they're not constitutional isomers because I still have a 1, 2, 3, 4, 5 carbon chain where the alcohol is at the second carbon. So for them to be constitutional isomers, the alcohol would have to be somewhere else, or it'd have to be like a 4 carbon chain that had a methyl and an alcohol, and we don't have that situation. So these are in fact identical. All right, and if you were to take this and just flip it over like this, right, this would 1, 2, 3, 4, 1, 2, 3, 4. That, if you flip it over like what I just did, it would look exactly like that. Okay, all right. Next up, here we have a 1, 2, 3, 4, 5 carbon chain, but now we have a 1, 2, 3, 4 carbon chain. So these, 1 chiral center and still 1 chiral center, but this is different, right? You have a methyl and an isopropyl. Here it was a methyl and a propyl. So these are different groups. So this is not enantiomers, diastereomers, or even identical. These are in fact constitutional isomers. Okay, they have the right to life, liberty, and the pursuit of happiness. All right. Okay, next up, for this one, so here what we see is both of these aldehyde functional groups, they're on the right side of the molecule. And so if you notice, this chiral center stayed the same. So this one didn't change, but this chiral center does change, right, from a wedge to a dash. And so what does that mean? We have two chiral centers here, and one changed, one didn't. They can't be enantiomers. To be enantiomers, every chiral center has to change. And so since they didn't, this would actually be considered diastereomers. If I misspell it, it's right there at the top of the page. Okay. So now when we look at these two, what do we got? We got two wedges, two dashes. All right, here's the kicker. You might be tempted, because I said, right, both chiral centers had to change for it to be enantiomers. But this is actually a meso compound, right? You've got both of these chiral centers where they have a plane of symmetry directly in the middle of them. So technically this molecule, if you were to take it, like imagine this my hand and see how I flip it this way. If I were to flip it over, this molecule would then look like this. So because these are meso, meaning they're achiral, they can't be enantiomers, right? If they're enantiomers, they have to have optical activity. They have to be chiral. So these would actually be considered identical. All right. Next up, what do we got? All right, we have a benzene ring, NHCH3, NH2. All right, so we do have two chiral centers here. All right, and luckily these two groups, like there's no way that we could have a plane of symmetry in the middle of these two chiral centers. So if you notice what happens, it goes from a wedge to a dash, so it changed. All right, it goes from a wedge to a dash, it changed. So all the chiral centers changed. That means these are a pair of enantiomers. All right. We look at this one. What does it go? It goes from wedge to dash, dash to wedge. So yeah, they both changed again. Yeah, and there's no plane of symmetry here. So this is just another pair of enantiomers. All right. Now let's look at this one. So the chiral center here, which would be most closely related to that one, right? The benzene ring. That has an NHCH3, while this one has an NH2. And then this one has the NH2, but this one has the NHCH3. So these swapped their nitrogen group. They both have chiral centers, but you changed the connectivity at those chiral centers. So this can't be enantiomers, diastereomers, and they can't be identical, right? Because both of them would have to have an NH2 here and an NHCH3 here, right? Or vice versa. So the only thing these can be are constitutional isomers. All right. Let's see. Next, what do we got here? Well, these aren't a mirror image of each other, right? They should both be dash here, and they should both be wedge here, or they should both be dash and wedge, right? To be mirror images. So what that means is if you were to actually take this, right, and flip it over to where you put the benzene ring on this side, right? So you'd have 1, 2, 3. You'd have your NHCH3 here and your NH2 here. And then what would happen when you flipped it over? This would become a wedge, and then that would become a dash because we flipped it over, right? So we changed the dash and wedgeness of them. So you notice wedge, wedge, dash, dash. So these two are actually identical. All right. And then our final two. It's the final countdown. All right, so what do we do here? We've got OH on the left, CHOH on the right. So this chiral center and this chiral center, right, are the ones we would compare. So we see OH is dash, dash. It didn't change. The chirality here doesn't change. But then we look here, this guy and this guy we're comparing now because they both have the CHO on them. And the rest of the backbone is the same. So this did change. So because one of the chiral centers changed and the other one didn't, we would call these diastereomers. Diastereomers. I misspelled it, but you get what I'm trying to say here. All right. Let's see. Next up. So, I think what I'm gonna do to make this easier, because this isn't set up as a really good. It's supposed to be like a mirror image, but so if this is the mirror image of that structure, then that would mean both of these would have to be wedged, and it's not. So what that means is if we were to flip this over, where the OH is here and the CHO is there, right? Then we would go from a wedge to a dash. We go from a dash to a wedge. And when we see that, when we get that, right, what do we notice? The OH changed, but the CHO didn't. Okay, so in this case, this is yet again another pair of diasteromers. All right, so this wasn't an exhaustive list, but I was at least trying to get you a fair amount of options here. So hopefully this helped. All right, adios and stay weird.